Testing, 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 testing. All right, we're good to go. Rolling. We have our backups going. Lining the defibrillators. Okay, we're good to go. Welcome to another Hoopo stream. Today we're doing something a little bit different. We're looking at two papers at the same time. So this is the first time we're doing this, but instead of just reading one paper super thoroughly, there's two papers that came up on my radar today that seem a little bit different initially, but are actually more alike than different after a little bit closer inspection. So basically this is 01 to 3, which is 0 shot, 1 image to 3D object out of Columbia University and Toyota Research Institute. 20 March 2023, so basically super recent. And then you also have text to room, extracting textured 3D meshes from 2D text to image models, coming out of TU Munich and University of Michigan. So both of these papers are going from generative art, right? Generative models, diffusion models, going basically 2D pixels into 3D. In this case, meshes. In this case, I think there's an intermediate nerf. But I wanted to look at these side by side, and especially given what we were doing yesterday with the nerfs and Nerf Studio and trying to get a nerf out of a mid-journey image, I think these should be a little bit more interesting because this is very similar to what we were doing yesterday, right? Kind of getting different views of an object from some of these generative AI art models. Let's go ahead and read the abstract and look at these figures for these two. We present text to room. This is very zoomed in. A method for generating room scale textured 3D meshes from a given text prompt. To this end, we leverage a pre-trained 2D text-to-image model. So probably going to be Stable Diffusion, if I had to guess, to synthesize a sequence of images from different poses. This is basically effectively what we were doing yesterday. In order to lift these outputs into a consistent 3D scene representation, we combine monocular depth estimation with a text condition in painting model. Okay, so actually, and we literally said this yesterday. We're like, hey, you know what we could do? We could feed these images into a depth model, and then that would be a better result than just the 2D. Here, they're also using in-painting, which is an interesting idea. Core idea of our approach is a tailored viewpoint selection such that the content of each image can be fused into a seamless textured 3D mesh. More specifically, we propose a continuous alignment strategy that iteratively fuses scene frames with the existing geometry to create a seamless mesh. Okay, so there's going to be a kind of process, some number of steps where they iteratively add images to the scene. Unlike existing works that focus on generating single objects or zoom out trajectories from text, our method generates complete 3D scenes with multiple objects and explicit 3D geometry, right? So this is that's a mesh. So something like a neural radiance field is also a way to store 3D information, but it's not explicit, right? It's implicit. It's like inside the neural net weights. Versus a texture with a mesh, that's explicit 3D geometry. That's 3D information directly in the form of vertices and planes with normal angles, and then colors that are specifically to those planes, and so on. We evaluate our approach using qualitative and quantitative metrics, demonstrating it as first method to generate room scale 3D geometry with compelling textures from only text as input. Cool. So that's the first paper. Let's look at the second paper. We introduce 0, 1 to 3, a framework for changing the camera viewpoint of an object given a single RGB image. To perform novel view synthesis in this unconstrained setting, we capitalize on the geometric priors that large-scale diffusion models learn about natural images. Our conditional diffusion model uses a synthetic dataset to learn controls of the relative camera viewpoint. Okay, so they have a fine-tuned diffusion model, which allows new images to be generated of the same object under a specified camera transformation. Even though it is trained on a synthetic dataset, our model retains a strong zero-shot generalization ability to out-of-distribution datasets. You know what this almost sounds like? This almost sounds like the computer vision version of in-context learning. Even though it's not at all that, because you're actually pushing gradients, you're fine-tuning on a new novel dataset, it's the same kind of idea, right? Where you can transfer learn into a new task by providing examples of that task without catastrophically forgetting what the original task that you were trained on is. Viewpoint condition diffusion approach can further be used for tasks of 3D reconstruction from a single image. Qualitative and quantitative experiments show that our method significantly outperforms state-of-the-art single-view 3D reconstruction and novel view synthesis by leveraging internet-scale pre-training. This is, I guess, just stable diffusion, but that's a cute way of saying it, right? Internet-scale pre-training. Okay. So we look at the kind of figures at the very first page. These are going to be the kind of eye catchers. So we have textured 3D mesh from text prompts. Generate a textured 3D mesh. So this here is a mesh, and then the texture is basically a 2D picture with pixels, and then that 2D picture has a specific way that it wraps onto the mesh. Using 2D text image, the scene is iteratively created from different viewpoints marked in blue. Okay, so these are the blue here. These little blue camera points that look like little pyramids. Those are cameras. You can see here iterative generation. Here you only have 3 cameras. Here you have 5, 6 cameras, another one here, and then by T20, so I guess step 20, you have a lot more cameras and you have iteratively generated this larger scene. We remove the ceiling for better visualizations. Yeah, so this is pretty cool, right? I think the in-painting is going to be the secret sauce for this one. We're going to skip through the related work and the introduction. Or actually, you know what? Let's look at the contributions in the introduction. So at the end of the introduction, generally, you'll have a bulleted list of contributions. Let's see if these guys have it too. They do not, but they have it in a little paragraph. So let's see these contributions. Generating 3D meshes of a room scale indoor scenes with compelling textures and geometry from any text input. Okay, so 3D meshes, which is textures and geometry, right? So the geometry is probably going to be in the form of vertices, right, that define a mesh, and then a texture that wraps, which is a 2D image that wraps around that specific mesh. Framework that leverages 2D text-to-image models and monocular depth estimation. So 2D text-to-image models is basically Stable Diffusion, Midjourney, anything like that. And then monocular depth estimation is getting a depth image from a 2D image. Monocular there just means you're doing it on one camera. So depth estimation with stereo vision is different, right? At that point, you're basically comparing a left and right image, and things that are moving more are closer to you and so on. But monocular depth estimation is more difficult because you have to kind of understand a little bit more semantically what's going on inside that image, and then make a guess about what is ahead and behind other things. Okay. Our proposed depth alignment and mesh fusion steps enable us to create seamless and undistorted geometry. Okay, so basically, maybe they have a 3-part pipeline here where they go 2D text to image, then monocular depth estimation, and then they use the depth that comes out of the monocular depth estimation to improve the mesh, and then the mesh improves the depth, and then there's probably some back and forth there. It's like a multi-objective optimization process. All right, the final contribution, a 2-stage tailored viewpoint selection that samples camera poses from optimal positions to first create the room layout and furniture, and then close any remaining holes, creating a watertight mesh. Close any remaining holes, that probably done. Actually, maybe this is where they use the inpainting, which would be very interesting to see. But there are kind of hard-coded algorithms that are quite old at this point that you could use to take a mesh or a point cloud and then close the holes in it. Okay. Look at the contributions of this paper. Primary contribution of this paper is to demonstrate that large diffusion models have learned rich 3D priors about the visual world, and even though they're only trained on 2D images. We also demonstrate state-of-the-art results for novel view synthesis and state-of-the-art results for zero-shot 3D reconstruction, both from a single RGB image. 3D reconstruction from a single RGB image. I wonder how they deal with the Yanis problem. Is this from the NISA group at TUM? You're talking about this first paper here. Yeah, it is. Is that how you say this weird like beta looking thing? Is that an S? So this would be Matthias Nieser. I'm not German at all, so. Let's go back down here. Finally, we present several quantitative and qualitative experiments to evaluate zero-shot view synthesis and 3D reconstruction of geometry and appearance from a single image. So both of these do have GitHubs. This one, okay, we got some code in here. This one has a live demo. Drop image, view from above, right, left, below, behind. Control camera position manually. You know what, why don't we have our mid-journey images that we were feeding into the NERF yesterday. Let's do this one. Download. All right, save it. And let's put it in here. Our cat from the front, and we want to see it from behind. And we do have, so Midjourney does have that notion too. We have save image. So this is the from behind that Midjourney generated, and you can see it like it understands the cat ears, but like these are very much cat ears from the front. So it doesn't know what the back of a cat ear looks like. Let's see what this model does here. Let's see if it really is state-of-the-art generation for the back of this cat head. Okay, back to it. Related work, we'll skip the related work and we'll just go straight into kind of the meat of the paper here. Okay, and here we'll skip the related work and go into the meat of the paper. Our method creates a textured 3D mesh of a complete scene from text input. We continuously fuse generated frames from a 2D text-to image model at different poses into a joint 3D mesh. So how do they get the depth from the 3D? Or from the 2D text to image? First generates the scene layout and objects, and then closes the remaining holes in the 3D geometry. For each pose in both stages, we apply an iterative scene generation scheme to update the mesh. So this is probably going to be a fairly complicated system with like many different steps here. So first align each frame with the existing geometry with a depth alignment strategy, and then triangulate and filter the novel content into the mesh. All right, you tell me, are these better or worse than Midjourney? Like they're almost worse, right? Like Midjourney got the line, right? Like cats tend to have these like kind of dorsal patterns, especially the Bengal cat that I was like trying to do here. So I don't know. This doesn't seem necessarily on par. Let's see what they're doing. Given a single RGB image, okay, have some RGB image with some height, width, and 3 pixels, where the dimension 3 corresponds to RG and B. Our goal is to synthesize an image of the object from a different camera viewpoint. Okay, R is sampled out of R. 3x3, this is rotation and translation. So this is the relative camera rotation and translation of the desired viewpoint. We aim to learn a model F that synthesizes a new image under this camera transformation. So you have some model F here. The model takes as input X, which is the image, right? The image of this cat. It takes as input a rotation matrix and a translation vector. But both of these together would be known as a transformation matrix. We denote XRT as the synthesized image, so this is the new image, which would be one of these here. We want our estimate to be perceptually similar to the true but unobserved view. Perceptual similarity. Something tells me they might be using clip. Maybe not. Okay, novel view synthesis from monocular is severely under-constrained. Our approach will capitalize on large diffusion models since they show extraordinary zero-shot abilities when generating diverse images from text descriptions. That is true. There are 2 challenges that we must overcome to create F. Although large-scale generative models train on large variety of objects in different viewpoints, the representations do not explicitly encode the correspondences between viewpoints. They do not, but there is enough human language contains enough information, right? There's enough signal in human language that words such as the front of, the back of, from the top, from the side, like those words actually work, right? And that's what we were looking at with Midjourney yesterday, right? Where if you actually look at our prompts, right? We had white Bengal cat portrait from behind, back of the head, right? we had white Bengal cat portrait 3/4 pose, and you see how it gives us that pose. We had white Bengal cat portrait shot, profile view, right? So even though these diffusion models haven't been trained explicitly with camera position, right? They do have some kind of implicit notion of what facing the camera means and what profile view means, right? So that is kind of what we're leveraging here, if you really want to think about it. That's the kind of information that is inside these diffusion models that this paper is trying to tease out. Secondly, generative models inherit viewpoint biases reflected on the internet. So probably what they mean by this is that there's a whole hell of a lot more front-facing shots of a human than there is pictures of the back of someone's head. So there's kind of a bias towards the front of someone's face. And this is probably what leads to the Janus problem. If you guys have ever heard of that. Images where basically you get this, you get like a face twice, right? So because there's a bias towards the front of someone's face instead of the back of someone's head, a lot of kind of generative 3D research ends up in this problem where you'll generate the front and the back end up being the same. Stable diffusion tends to generate images of forward-facing chairs in canonical poses. These two problems greatly hinder. Since diffusion models have been trained on internet-scale data, their support of the natural image distribution likely covers most viewpoints for most objects, but these viewpoints cannot be controlled. Yeah, it covers most viewpoints, but they're also going to be biased towards the front-facing shots. Then we unlock the ability. To this end, given a data set of paired images and their relative camera extrinsics, so this is the camera extrinsics is basically the position, pose, the transformation matrix of the camera relative to the object, relative to other cameras. Fine-tunes a pre-trained in order to learn controls without destroying the rest of the representation. This is important here, right? Where when you fine-tune a deep learning model on a new task, right? So you have some original task that's in the pre-training, and then you try to transfer learn it by fine-tuning it on a new task, you can run into what's called catastrophic forgetting, which is basically you're overwriting the weights inside the model that made it good at the original task, and thus every gradient step that you take that makes it better at the new task is making it worse at the old task. Use a latent diffusion architecture. Latent diffusion here basically refers to the diffusion, right? Diffusion is the process of adding and removing noise. That's how diffusion models work, is they try to model this noise that gets added and then removed, and then they can remove noise from basically noise and then create objects out of thin air, or create images out of thin air. But because images tend to be pretty high dimensional, it's really popular now to do this diffusion in the latent space. So the latent space of a neural net is basically a compressed vector representation of an image, and that is going to be much lower dimensional than the actual image itself. So diffusing in a latent space is popular for its speed. Then encoder, you got the encoder, you got the denoiser UNet, and a decoder D. At the diffusion time step, 1000, what? So diffusion models you have to basically run them a bunch of times in a row. You have to perform a bunch of inferences in a row. Those are called usually T, or time step. And 1000 is pretty high. Like, that's going to take a long time. You have to perform 1000 inferences with your diffusion model. So that's one of the reasons GANs are making a comeback, is because GANs are much faster. You'd only need to perform inference once. Let CXRT be the embedding of the input view and the relative camera intrinsics. Okay, so they're converting. They have some C model. They haven't really told us what C is, but C takes as input the image and then the transformation of the camera, and then embeds that, or creates basically a little vector out of that. probably just going to condition the diffusion model on that. We then solve the following objective to fine-tune the model. Okay, so this is the objective that the model is following, right? You want to find the theta here, the theta that minimizes this expected value here. And the theta is basically going to be the parameters of a neural net. Here, in this case, the parameter of the UNet, right? So this UNet has a bunch of parameters, theta, and you want to find the theta that minimizes this term here. And what is this term here? This term here is, get out of this. This term here is an L2 loss, right? You see these two parallel bars here, and then this little 2, 2 here. What that means is basically you're taking this term minus this term and then squaring it, right? And here you have z from e of x, t, and then e n 0, 1. So this is a normal distribution here. Normal distribution centered around 0 with a standard deviation or variance of 1. That's the noise, right? T is the amount of time steps. And then z of t here is the latent, right? So you have some encoder, capital epsilon, that takes the image x and turns it into a latent vector z. And that latent vector z is where the noise is actually being applied and removed. So here you have your UNet. You have the UNet is conditioned on the latent. It's also conditioned on the time step. And you see here, it's also conditioned on this embedded relative camera intrinsic. So this is very, very similar to other diffusion models that are being guided with other things, right? So this is a very similar equation to, for example, let's say you had a diffusion model that was guided based on a classifier, right? And you would have different categories within that classifier. You would basically have epsilon theta, zt, t, and then there would be some class vector here, or maybe some text here, or something like that, right? So basically, this is doing the same thing, except now you're conditioning it on the embedded version of your camera intrinsics. I wonder how they're embedding this, right? I wonder how they're actually getting the embedded version of the camera intrinsics. After the model epsilon theta is trained, the inference model F can generate an image by performing iterative denoising from a Gaussian noise image conditioned on that. Yeah. Okay, so I feel like this sentence right here is this entire paper. Main result of this paper is that fine-tuning a pre-trained diffusion model in this way enables them to learn a generic mechanism for controlling the camera viewpoints. Yep. All right, so let's actually look at these figures. How much knowledge of machine learning should I have before jumping into Kaggle competition? 0. Just try it out. Even if you don't succeed, you will learn a lot by trying to solve a real-world problem. It's really hard to win anyways because the leaderboard is usually people with lots of compute money to throw around. Yeah, don't actually try to win Kaggle competitions, man. That's very, very difficult to do because the people at the top, you know, like they're training on like 8 A100s. So you're very rarely, unless you're like you yourself have a ton of GPUs, are you going to be able to beat someone on a Kaggle competition. But that's not what Kaggle is about. I feel like Kaggle to me is about learning and about trying and about just seeing how people do it, right? You're basically solving a problem with a community of people. So yeah, I would just go ahead, find a problem that you think is interesting, do some exploratory data analysis, see what other people are doing, and see if you can get a little baseline going. Okay, let's go back to these figures. So got here the Gaussian noise. This is actually misleading. So the Gaussian noise would be in the latent space. This makes it look like it's a 2D image and the Gaussian noise is coming from 2D image, but the Gaussian noise, because this is a latent diffusion model, would be in the latent space itself. You have the input view. So this is the actual RGB image here, right? This computer. Here you have the rotation and translation matrices. Sometimes combined, they're called the transformation matrix. This is being used to condition the latent diffusion model, and then the latent diffusion model is going to take a bunch of steps, right? It's going to iteratively remove the noise over the course of a bunch of steps, t, and then you're going to get the output view. Okay, figure 4D, or figure 4, 3D reconstruction with 0, 1, 2, 3. 0, 1 to 3 can be used to optimize a neural field for the task of 3D reconstruction from a single image. During training, we randomly sample viewpoints and use 0, 1 to 3 to supervise the 3D reconstruction. Okay, so now that they've trained, they have some synthetic data set that has specific camera poses, right? So this obviously looks like a rendered CGI. Right? This is like some 3D object that they have inside Blender or something like that. And then because it exists inside that Blender, that game engine, right? That CAD engine, whatever you want to call it, 3D engine, you know the exact position of the camera, which means you can collect a data set where you have images of this object from every single camera position, and you know the exact camera position, right? So if you have that and you train a diffusion model on that, which is what they do here, then that diffusion model is quite useful for creating 3D reconstructions, because now you can say, hey, here's an object that I have, give it to me in a bunch of different viewpoints from a bunch of different viewpoints, and then I'll feed that into a nerf or something like that, which is literally exactly what we were trying to do yesterday in our video. You guys should definitely check out the video yesterday. We did a little bit of hacking and trying to see if we could get Nerf Studio to create a image or a nerf for our cat based on Midjourney images. You see here the back of the chair, kind of like a top-down shot, different profile shots. Okay, let's go back to this one. Okay, so what were we doing in this one? So in this one, our scene is represented by a mesh. Okay, so a mesh is an explicit form of 3D information, right? It's an explicit 3D store, and it contains things like vertices, which are n by 3, right? So there's n amount of vertices, every single little point in one of the meshes, so is a point in 3D space. That's where the 3 dimensions here comes from, and then n, because you can have any amount of points in any amount of vertices. Vertex colors. So this is, for each vertex has a color, and then the face set S. Okay, so this is different than what I thought. So there's different ways of explicitly storing meshes and textures. One that is very common in video games and in 3D art is where you have a mesh and then you have basically a 2D texture, and then there's an additional kind of mapping of how that 2D texture gets applied to the mesh, right? So 2D texture applied to mesh mapping. You guys have probably seen these before, but this is, yeah, like this is a good example. Oh, not that. This, right? So the way that a lot of textures are mapped onto meshes now is you basically have this, right? You have this kind of like mapping function, right? UV mapping that basically says this part of this 2D image corresponds to this part of this 3D texture or 3D mesh, and then you wrap it into it. But another way of doing it is by just storing the vertex colors, is by saying, hey, we're not going to do this like kind of weird, complicated like 2D texture. Instead, every single point in this texture or in this mesh is going to have a specific color associated with it. So then we don't need to keep track of this kind of mapping function. Okay. Input to our method is a set of arbitrary text prompts. Okay. T equals 1 to t. that correspond to our selected poses. E sub t z from t equals 1 to t r3 by 4. So this r3 by 4 here is a transformation matrix. So that's the same as this here. Right, so this tuple here of r comma t, this is rotation translation. That's the same thing as this here, this e t r3 by 4. Right? This is just a different way to represent it. Hello, food station. Howdy. Inspired by recent methods, we iteratively build up the scene following a render, refine, repeat pattern. I don't know if that's necessarily a recent method. I feel like this kind of like iterative refinement is something that's really old, you know, in computer vision. People have been doing that for a very, very long time. Slam is kind of a form of iterative refinement if you think about it, right? Because in Slam, you're kind of like using your guess of where you are to update the map, and then using the map to update the guess of where you are, and then you kind of go back and forth and back and forth, and kind of this iterative loop over and over again. I got some Doritos and watching this stream. Nice. Nice. Okay, we summarize the iterative scene generation process, typically formally for each step of generation T. So this is different. So the T in this paper, this T is basically the diffusion T. So there's basically a bunch of steps in a diffusion model, right? But the T here, I think, just represents the time step of the iterative process that they're talking about here, where they do the mesh, and then they do the depth, and then they do the mesh, and then they do the depth. So R is a classical rasterization function without shading. I of t is the rendered image. D of t represents the rendered depth, and M of t is the image space mask. Okay. So this is not actually like this equation is not really an equation, to be honest. This is basically just saying that you have some R here, right? Which is the render, refine, repeat process. The process takes in this M, which is the mesh. It also takes in this E, which is the poses, right? And then it's going to output images, it's going to output depth images, and it's going to output image space masks. But this R is not just like one function, it's like a process. There's a couple different, or no, maybe not. Maybe R is the classical rasterization function, so that's actually how they get the, wait up. Okay. People are texting me for some fucking reason. And I just highlighted everything. Gross. Okay, let's look at, actually, let's keep going here. There's more math. We then used a fixed text-to-image model, FT2I, so this is probably going to be a stable diffusion here, to inpaint unobserved pixels according to the text prompt. Okay, so unobserved pixels, there's going to be holes in this mesh, and then they're going to ask the stable diffusion model to paint in those holes. And you have here the image. What is P of T again? Arbitrary text prompt, so this is the prompt here. What is M of T? M of T is the mask. So you have your mask, you have your prompt, you have your image, and then the F text to image here, which is probably a stable diffusion, is going to give you your new image, which should fill in any of the holes that aren't in this mask. We inpaint unobserved depth by applying a monocular depth estimator, FD, in our depth alignment. So this is going to be a separate model, right? So you have your your stable diffusion model here. This is a text-to-image generative model, and then you have a monocular depth estimation model, which takes in an image, maybe some extra information, and then outputs a depth, right? A depth image that corresponds to that image. So this is an example of what that would look like, right? You have an image here of this kind of kitchen scene, and that gets fed into this depth model, which gives you the depth image. These depth estimator models, like, kind of misleading sometimes. Like, they work well in certain domains, like the ones that do monocular depth estimation for like autonomous vehicles, very good. But it's also because all the autonomous vehicle data is very similar, right? There's always this kind of like vanishing endpoint of a road in front of you, so it kind of does really well. But monocular depth estimation for like weird scenes and weird angles of a weird thing, like, generally they don't work super well. So I'm kind of fascinated by the fact that they got it to work super well here. Maybe I'm just underestimating how much progress has been made in monocular depth estimation. Finally, we combine the novel content. So the image with the holes in painted, the depth with the from that image, and then M of T, which again is our image space mask for the existing mesh with our fusion scheme. Okay, so now that you have your, you know the camera position, right? If you know the camera position and you know the depth, that means that really you actually know a bunch of points. Each one of these pixels has a depth associated. So now you basically have a point cloud, right? And you can fuse this point cloud into the mesh, right? Because the mesh itself is basically just, it's basically like a point cloud, right? It's a bunch of vertices, except the vertices also have colors, and they also have faces, so you know which vertices are connected to which other ones. But once you have a point cloud, there's a lot of different ways to go from point cloud to mesh. We iteratively create a textured 3D mesh in 2 stages. First, we sample predefined poses and text to generate the complete scene layout and furniture. So there is a little bit of a kind of hard-coded thing here, right? What is the predefined poses? Who comes up with those? Each new pose, marked in green, adds newly generated geometry to the mesh, depicted by green triangles, and an iterative scene generation scheme. Blue poses denote viewpoints that created geometry in a previous iteration. B, second, fill the remaining unobserved regions by sampling additional poses marked in red. Okay. So they have some text, some prompt. They also have camera poses. And then they're saying, here's my camera pose, here's my text, I'm going to generate an image. Then I'm going to take that image and I'm going to get the depth. Then I'm going to take the depth and I'm going to use it to create a mesh. Then I'm going to find the holes in my mesh. Then I'm going to have a mask that represents the holes in the mesh, and I'm going to ask the generative model to generate another image that kind of looks over, that will fill in what's inside that hole. Then I'm going to feed that back into the depth, and I'm going to get another kind of depth image that I can convert and fuse into my mesh. So it's kind of this iterative process. Kind of like that. I feel like, right, we should do that with this, right? I mean, these are both getting to kind of similar-ish things, but if you have, the thing with this one is you have very, very precise camera positions, right? So like, if you have a bunch of images of an object with very, very precise camera positions or camera poses, because it's also rotation and translation, it's not just translation, it's also rotation, then you can feed that into a nerf, or you can feed that into, there's a huge variety of different things that, given different views of an object, if you have very good camera position, you can basically get a 3D mesh from that. This is more of like a combined system, I would say. It's kind of like there's all these different pieces kind of feed into one another. It's harder to kind of pick out an individual piece and use it, versus this one is a little bit more piecemeal. You could just use this part here. You could just use this part here. Let's go back here. Iterative scene generation. For each new pose, we render the current mesh to obtain partial RGB and depth renderings. We complete both utilizing respective in-painting models, right? So in-painting, that's why they have this mask, right? This mask M of T is because the in-painting model needs to know specifically which part of the image it's generating. Next, we perform depth alignment and mesh filtering. These are probably just done in generic way. There's a lot of previous research on going from depth images into meshes and scene reconstruction from depth. To obtain an optimal next mesh patch, which is finally fused with the existing geometry. Right, so you do some in-painting, you get the depth, you apply the mask that you use for the in-painting to the depth. That gives you a very constrained, tiny little point cloud that just represents exactly what you need to add to the mesh, and then fuse it. There's a lot of like clever fusing, you know, like I don't know if they're doing it here, but like for example, you see here how this bookcase is kind of like warped and weird looking. A lot of like scene reconstruction and like mesh fusion and these kind of like map creation algorithms, like they can have a lot of different priors that you put in them, right? Like there's a prior like that the floor is generally going to be flat. There's a prior that walls are generally going to be flat. There's a prior that surfaces are more likely to be kind of like this, perpendicular, than maybe like this or anything like that. So these scene reconstruction models, generally, if you can add more of these kind of strong priors about like flatness and just things that we know from operating in the world, then you get better results. I think if they were constrained to the inside of rooms, they could have used some of those stronger priors to make the mesh refinement stronger. Right? The only reason you wouldn't want to have like a kind of flat surface prior somewhere in your mesh refinement is if you also wanted to use this for natural scenes that don't have flat walls. Lift a 2D image eye into 3D. We predict the per pixel depth. This is the monocular depth estimation. To correctly combine old and new content, it is necessary that both align with each other. In other words, similar regions like walls or furniture should be placed at a similar depth. However, directly using the predicted depth for back projection leads to hard cuts and discontinuities, since the depth is inconsistent in scale between subsequent viewpoints. This is true. Monocular depth estimation, right? The actual, not only is it kind of magic that it works to begin with, but the actual depth that it gives you, right? Depth is just going to give you a normalized, it's just going to give you a number from 0 to 1. It's going to be saying this stuff here is closer than that stuff there. But if it's not going to be like accurate, right? It's not going to be like, oh, this is 1.7 meters from here, right? It's just, you just have a notion that it's further away, but it's not like super accurate. And that's kind of what they mean here, is that it's going to be inconsistent in scale for different camera points and different images. Perform depth alignment in 2 stages. We use state-of-the-art depth in painting that takes ground truth depth for known parts in the image and aligns the prediction to it. Okay, so this here, they have some model, FD, which is they're calling it the state-of-the-art depth in painting network. It's taking in the ground truth depth, which is not actually ground truth, right? It's just basically the depth image from a previous camera pose. And then it also takes in the image, and then it gives you the kind of like better prediction for that. We improve the result by optimizing for scale and shift parameters. Okay, so you have some gamma and beta here. Aligning the predicted and rendered disparity in the least squared sense. Okay, so this is some additional regularization that they're doing here to ensure that the depth images from the different camera Positions are consistent. We mask out the unobserved pixels. We can then extract the aligned depth. Right, so you're taking your depth here, d hat sub p, right, which is your predicted depth, and you're basically scaling it, right? So this actually looks, this is very similar to a neural net, right? You have weights and then a bias, and this is the same thing. It's just a linear transformation here. You have linear scaling and then offset. Finally, we smooth d hat by applying a 5x5 Gaussian kernel at the mask edges. So what does this mean? So a Gaussian kernel is basically a convolutional kernel. GIF, I love this GIF. But, right, so in a convolution network, you have this kind of kernel that goes over an image, right? Like this. But boom, boom, it's like going over the image. So there is what's also called a Gaussian kernel, right? And a Gaussian kernel, see if I can find Gaussian kernel for image noise. Yeah, maybe one of these. But basically you're convolving like a Gaussian across, in this case, the edges of the mask. And what that's going to do is it's going to smooth it out, right? It'll basically like average all the values, and then that'll make it a little bit more smooth. But this in itself is also a kind of prior, right? You're making this assumption that depth is going to be smooth and more continuous, right? But that's not necessarily the case. If I was taking a picture of a some kind of spiky like texture or something like that, you wouldn't want to do this. You wouldn't want to apply a 5x5 Gaussian kernel at the mask edges because it would basically smooth it out. So this, in a sense, is a form of kind of a prior, right? That they're making the assumption that the depth should be smooth when maybe it shouldn't be. But that's kind of deep learning 101, right? Is like trying to figure out what assumptions you can make, what priors you can use that result in better performance for your specific use case. Virtualization of our mesh fusion step. We triangulate an image such that the 4 neighboring pixels, orange dots, create 2 faces. Do you read textbooks on ML? Not really. Not really recently. Maybe a long time ago, but not on stream. Do you have one in particular that you are interested about? We filter a face marked in red if its surface normal forms a small grazing angle with the viewing direction, or if any edge in the world space is too long. Okay, so this is actually how they're doing the mesh fusion here. So A, pixel triangulation, face filtering, and then mesh fusion. Okay, so what exactly is going on here? They filter faces if its surface normal forms a small grazing angle with the viewing direction. So in a mesh, triangles, let's see if we can get a nice picture of a mesh. Yeah. So in a mesh, right, you're going to have these triangles, right? And those are called faces. And those faces have a normal vector, which is basically just the vector that points kind of perpendicular from that face, right? So what they're saying here is that they're going to look at these faces And if the surface normal, right, which is that vector with respect to the viewing direction, right? If it's just like not, if the way, basically what they're trying to filter out here is that if the normal with respect to the view direction is like not good enough, then you basically want to get rid of these faces, right? And then an additional kind of constraint here they have is the edge in the world space is too long. So you don't want to have edges that are too long. So here you see here the edge here versus the edge here. You see how much longer this edge here is? And they basically don't want very, very long edges, which is another prior, right? It's like there's a lot of kind of like secret tiny little priors that they're putting in here. We fuse the remaining faces marked in green with the existing geometry marked in blue. Okay, so your depth image gives you a bunch of vertices. Those vertices are connected together into faces, and then those faces and vertices are fused into the already existing mesh, and that's what the mesh fusion step is. We insert new content. You have your image, you have your depth, and you have your mask. Right, your mask cuts out specific parts of the depth in the image. Into the scene, for that, we first back project the image space pixels into a world space point cloud. Right, so if you have depth and you have images, and you have a mask, the mask cuts out a specific part of the depth image, then the depth image is aligned to the color image. So each pixel in the depth image, of course, has a corresponding color. So you could basically turn that into a point cloud, right? Now, because each point, each pixel in the depth image corresponds to a point, and you have basically RGBD, right? K are the camera intrinsics. So camera intrinsics is kind of like distortion is one way to think about it, but it's basically a bunch of numbers that represent the camera geometry, right? So camera intrinsics is, so a camera, there's basically a bunch of geometry that describes how a camera acts, right? There's things like the focal point, the focal length, principal point. There's kind of these distortion parameters, right? Like cameras have lenses, and these lenses distort the image so that certain parts of the image are going to be warped, right? And all of those can be basically compressed into this matrix, this 3x3 matrix that's called the camera intrinsics, right? So camera extrinsics is the position of the camera, right? The position and rotation of the camera in the world. Camera intrinsic is basically the distortion and the appearance of the images that result from this given camera. So you have here your camera intrinsic parameter, you have W and H, which are your image width and height. Then they have a simple triangulation scheme where each of the 4 neighboring pixels, so you have 4 pixels here, right? So U and V, so this is 4-point connectivity here, form 2 triangles. So if this is one of your depth points, you have this one here, then this one here, then this one here, then this one here. So for each pixel, which is a point in your point cloud, right, because you have the depth, and that's going to form 2 triangles. So there's a little bit of a prior there as well, where they're basically saying, hey, if you have 4 points, you basically connect them such as so, and now you have 2 faces and they're connected. But you know, it's not necessarily the case that every single point is going to be connected to the previous point. There could be discontinuities in your real world scene that the depth image doesn't really account for. This naive triangulation creates stretched out 3D geometries. To alleviate this problem, we propose 2 filters that remove the stretched out faces. First, we filter faces based on their edge length. We remove a face if the Euclidean distance of any face edge is larger than a threshold. This isn't great, but basically they have some specific threshold, some hard-coded number that they designed, where if any of these edges here on the mesh, right, so if any of the edges on this mesh are too long, they're just going to cut them, right? They're just going to say, hey, well, actually, let's just cut these. but seems like a very weird, like that's just going to be hard coded very hard. It's just going to be very specific to the application. I don't know. I generally don't like these kind of hyperparameters. And then they also do this filtering based on the surface normal and the viewing direction, right? So S is the face set, which is the set of all the faces, right? And the faces are just basically coming from the pixel of the vertices, which are themselves coming from the depth and the pixels. Any good book suggestions that you have read in the past? I liked Chalet's book was great, but that is really old at this point. Books are kind of outdated. Yeah, maybe an unpopular opinion, but I feel like books are old, you know, like I definitely read a lot when I was younger, but the older I get, I feel like I read less and less because I feel like the information speed of the world is just so much faster now that a book just takes too long, right? It's like if you instead of spending 40 hours reading one book, if you instead spent those 40 hours reading papers and blogs and doing coding and like trying out Kaggle competition, like you're going to grow a lot more and learn a lot more from being involved and kind of like actually working on things and reading smaller digestible things like blogs and papers than you are by kind of going through one giant book. So maybe if you really, really want a book, try to find a book that has examples in it so that you can work on those examples. But big giant books that don't have any examples and you're just sitting there just reading for like 40 hours straight, I don't think you're going to get very much out of that. Okay. So we have our face set. Well said. You should write a book on swag. I0, I1, I2 are the vertex indices of the triangle, right? So these are 3 points. I0, I1, I2 are going to be like I0, I1, I2. So you see here how they form this triangle, which is a face. This is the magic threshold number that they hard code. Normalized face normal. So this is the vector that points out of the face. And it's normalized, right? So it has a unit length. And then V is the normalized view direction. So N, T, V here. So you have the normal vector and you have the view angle. So here you're multiplying two vectors, right? If that is above some threshold, then include it inside the face set. If it's not, then remove it. So this here is basically the filtering, or is one of the filterings. They also have a different filtering, which is this delta edge. So another filtering function here would be I0, I1, I2, given I0 minus I1, or I1 minus I2, or I0 minus I2 are all less than delta edge. So that would be the other filtering function. Finally, we fuse together the newly generated mesh patch and the existing geometry. All faces that are back projected from pixels falling into the inpainting mask MT are stitched together with their neighboring faces, which are already part of the mesh. Precisely, we continue the triangulation scheme at all edges of MT, but use the existing vertex position to create the corresponding faces. So one thing here that I'm seeing as a potential problem is that there's kind of this assumption that every previous step of the mesh refining is ground truth, right? Where they're generating an image based on the holes in the current image, right? But by doing that, there's kind of this assumption that, okay, well, I'm only going to generate images based on this mask that inpaints the holes. But what if the mesh that you had before, right? What if your current mesh actually has problems with it? Then you're just basically you're never actually going back and fixing the problems with that mesh. And I think that a lot of mesh refinement that algorithms that you see kind of historically, they try to solve that problem. So I don't see an attempt to solve that problem where if you have any errors in your current mesh, this current approach is just going to continue to basically just keep that rolling, right? You're never going to go back and correct the errors in the mesh, right? Like maybe for example here, you see how here there's this kind of like weird, long, wavy, like white patch that obviously feels like something happened here with this bookcase, right? It didn't quite get this bookcase. But you see how their final solution still has that same white, wavy patch because at no point was there any kind of additional part of this process that looked at this mesh here and said, hey, you know what? This mesh actually looks really gross and it doesn't agree with my other guesses of this mesh. And then there's I'm getting a lot of different answers for what this should be. So I don't know, something there to think about. Maybe they needed a little bit more like agreement from multiple, not just in painting and not just assuming that the current mesh is ground truth. Okay, the generated scene can degenerate and contain stretch and hole artifacts. This is kind of exactly what I've been saying. If the poses are chosen carefully, or if you don't go back and fix them, or if you don't go back and kind of regenerate areas that you already know and then kind of refine them over time and prevent the scene from degenerating. So instead of kind of having this additional regularization, maybe some additional step in the mesh refinement that ensures consistency, instead what they're going to do is they're going to make sure to choose the poses carefully. So they're going to be doing this here, two-stage viewpoint selection strategy that samples each next camera pose from optimal positions and refines empty regions subsequently. Okay. Let's skip over to our other problem. Because I wonder if these guys are doing something similar, right? Are these guys being clever about how they pick the camera poses in their synthetic data set? We use the recently released Objaverse dataset. What is this? Objaverse, a universe of annotated 3D objects. Okay, so basically just a giant 3D object database, kind of like a Sketchfab type situation. Large, open scale, open source dataset containing 800,000 3D models created by over 1,000 different artists. Has no explicit class labels. Like ShapeNet, Objaverse embodies a large diversity of high-quality 3D models with rich geometry, many of them fine-grained detail and material properties. For each object in the dataset, we randomly sampled 12 camera extrinsic parameter matrices. Okay, so there is no clever selection of camera poses here. Yeah, so there could have been something more clever here, right? Because at the end of the day, I feel like there's some distribution of camera angles with respect to objects that is not uniform, right? Most of the time when people take pictures, they're taking pictures of the front of something, or when you're giving something like this, like a picture of a cat, and you want to look at it from a different view, generally people aren't going to want some weird arbitrary viewpoint. They're going to want like the back or the side or something like that. So I don't know exactly what I want here. I don't know exactly what kind of prior I'm trying to introduce in the selection of poses, and maybe a uniform distribution over all possible camera poses is the better way to do it, but I don't know. I feel like there's something here. There's something that could be done here. Two views can be sampled for each object to form an image pair, X and XRT. corresponding relative viewpoint transformation that defines the mapping between both perspectives can easily be derived from the two extrinsic matrices. So they have two images. They have X and then they have XRT. They have this tuple of two images. There's some relative position between those, right? So there's a camera that took image X, and then there's a camera that took image XRT. And because this is all inside a 3D engine, right? These are all little 3D models. You know exactly what that transformation is because you know the extrinsic matrices of both of those cameras. So you can basically find the relative transformation matrix between the two transformation matrices of the cameras. Can thus be considered zero-shot results. Okay. Yeah, so this is where I thought they were going with the view perceptual consistency is people have been using clip as a way to measure the consistency of an object perceptually, but there's problems with this, right? Where basically the distance in clip embedding space between two images is not, I think, necessarily a good proxy for is this object from the front and the back the same? We invert the order while still retaining the identity of the object. This way, the uncertainty due to self-occlusion can be modeled by a probabilistic generative model when rotating around objects, and the semantic and geometric priors learned by the large diffusion model can be leveraged efficiency. Why is this not working? Semantic and can be leveraged efficiently. There you go. So this is important to know as well, right? Is that these diffusion models already have some kind of semantic and geometric prior to camera angle, right? Because you have profile shots, side shots, and so on. So here they're only just making it even more explicit by fine-tuning it on these camera transformation matrices. See here a minion from different poses, Lysol bottle from different poses. These are cherry-picked. Notice how they don't show you what the underneath of this car looks like because it probably looks terrible. Method works are robust objects with different surface materials. We randomly sampled 5 different viewpoints and indirectly showcased the results without cherry picking. I don't know about that. Looks like you're cherry picking. Right, like look at the underneath of this. You see how the model has kind of no idea what the underneath of a Lysol container looks like. Same thing here. It probably has no idea what the underneath of this car looks like because there's very, very few images of the underneath of a car. Okay. Baselines, they're going to compare this to a bunch of crap. Let's just keep going on the figures. Diversity of novel view synthesis. With an input view, we fix another viewpoint and randomly generate multiple conditional samples. The different results reflect a range of diversity in terms of both geometry and appearance information that is missing in the input view. Okay, so they show you how obviously there's some hallucination here, right? You're reconstructing from limited information and you're not going to get the same results if you use different seeds. Right, so sometimes the diffusion model thinks that the lens pops out. Sometimes it thinks the lens doesn't pop out. There's quite a lot of variance here. Qualitative examples of 3D reconstruction. The input view images for each method, we are rendered a different angle and reconstructed 3D mesh. Ground truth meshes are shown on the right. Okay, so they do have the ground truth mesh because this is a synthetic data set of 3D objects. So they know exactly what the mesh is. This is with their technique. So I don't know exactly what they're doing. I'm assuming they're using the same 3D reconstruction technique for every single one of these, right? These are different. Maybe these are different construction techniques. I think we read the point E paper on this channel. I don't know, these all kind of look about the same. I wish they would have used the same objects, right? Would have made it easier to compare. Or maybe these are the same objects and this is just that bad. Yeah, these are the same objects. All right, never mind, I take that back. So we see here this little truck. This looks a little bit better than the pointee. Pointee has a lot of holes in it. SJCI looks like garbage. And MCC looks like garbage. This is cool. So now, rather than using a ground truth image like this, or an image for an object that they have the ground truth mesh for, they're just going to basically get an image from a text to image model computer from the 90s in the style of vaporwave. You get the image, and then they feed it into their pipeline here and generate these novel views. So, I mean, there's some stuff here that's interesting, right? So, like, you see how here this mouse has like a little tail that goes down. So there is kind of an understanding here of like the mouse and the keyboard, right? Like that is some kind of 3D understanding where like if you look at something like this, then you look at it like this, like the relative position of these things, right? Like from different viewpoints should be maintained, which is kind of what's happening here with this mouse and this keyboard. But some of it isn't as good. Like if you actually look at this undershot, right? The underneath angle, this makes it seem like the keyboard is underneath the monitor. So it's kind of lost the relative positioning of that in there. Right, let's look at the figures here. Okay, so these are the results for the scene reconstruction. This is the prompt that was used. So this is the prompt that is used every time they render an image. And then they're going to take that image from this prompt, and then they're going to get the depth, and then they're going to use the depth for that to create a point cloud. Then they're going to use that point cloud to make a mesh, and then they're going to move the camera just a little bit, and then they're going to do the same thing again, except they mask out any already existing information and only render new information. So, I mean, this isn't super great, you know, like there's a lot of artifacts here, like very wavy and shitty, but at least it's you know, it's complete. There's no holes in this mesh, right? Because they fill in every single hole. I feel like an extension to this work would be some kind of method that refines these meshes a little bit more rather than just kind of first one that you get is the first one that you get, which is what's currently doing. These are pretty rough, but turns out like diffusion models are pretty good. Like this is the original diffusion model image. Living room with a lit furnace, cozy curtains, bright lamps. I guess there's a lot of data of room interiors, so it makes sense that generative models are pretty good at room interiors because there's just so much data on the internet of room interiors. Qualitative comparison of our methods and baselines. Okay, so here they're comparing against pure clip nerf, which is probably some kind of nerf technique that uses clip. Cannot produce immersive scenes with floors and walls. Outpainting does not produce 3D consistent scenes. Text to light and blockade both have holes due to occlusions. In contrast, our method creates complete meshes without holes and high details. We remove the ceiling in the top-down view for better visualization of the scene layout. Yeah, so you see these holes in the center here. That's because that's where the camera is, and the camera's kind of doing this like 360, but it doesn't ever really look down. Right? So text to light, blockade, these techniques, you see that artifact of just like the empty floor where the camera is like centered and where it rotates. But the technique in this paper, they don't have that artifact. They don't have that like floor hole because they move the camera a little bit more. Yeah, both have holes due to occlusions. Our method creates complete meshes without holes. High details. Okay, so do a couple ablations here. Depth alignment. Monocular depth prediction from subsequent frames can be inconsistent in scale. This leads to disconnected components in the mesh that are back projected from multiple viewpoints. Our depth alignment strategy allows fusing multiple frames into a seamless mesh. Stretch removal creates undistorted scene geometry. I don't know about that. It still seems pretty distorted. And I think naively filtering based on edge length and normal angle is primitive, not complete. I feel like there's better priors you could use that aren't as hard-coded. Two-stage generation creates complete scenes. Our approach chooses camera poses in 2 stages to create a complete scene without holes. After generating the scene, still contains some holes. Okay, so here's ablation study. An ablation study is where they remove specific parts of a process, and then you see which parts of that process are the most responsible for the success, or maybe they're not, right? So one of the things that you can discover in an ablation study is that like some trick that you're using actually doesn't help at all. So here they have without the depth alignment, they have without the stretch removal. What is the completion? I guess this is the selection of camera poses that look at specific parts of the mesh that have holes in them, I guess. So stretch removal, yeah, you can see how if the edges are too long, it removes them, so it kind of removes these like long edges. Without alignment, right, then you don't have, this looks, I don't know, all of these look kind of bad, to be honest. Because this room is probably square, you know, it's not whatever this weird shape is. GNG, to be slightly off topic, QSTN. The biggest problem for running a model with 102 power quantum computers solve this medium term? No. Quantum computers are still far away, but yes, in theory, they can perform more computation than current computers, but they do it in a weird way, so it only applies to specific problems. I don't know anything about neural nets specifically designed for quantum computers. Yeah, I think that there probably is. I don't know of them, but there's probably people who are doing research on how to fit neural nets into quantum computers, and like different types of neural net, different types of back propagation, different types of gradient descent, right? Activation functions. There's all these like concepts that we have around neural nets, and I think we have ways of doing that with our current computers. And there's probably ways where you can basically do all of that significantly faster or in a parallel way on a quantum computer. I just don't know anything about that. But talking to people who have a little bit more knowledge on quantum computers than I do, it seems like it's still quite far away. I think we're like, I don't know, perpetually 10 years away is my guess. Okay. So I mean, that's basically it for these papers. Let's check out the corresponding GitHubs. So we got text to room. Look at the insights. Let's look at the contributors. Go to this one. Look at the insights. Let's look at the contributors. Okay, so text to room, basically just all this one dude, Lucas Hall. And he basically pushed the entire repo in one day. So it's like just him, and he basically dumped all of the repo in one day. We look at this other one here, very similar. You basically have this guy here, Roshi Liu, and then you have maybe two like kind of helper people, Colombia, USA, Belgium, New York. So you have like kind of three people, but they're basically it's the same thing as they just pushed it. So these aren't like active repos that and libraries where you have a bunch of people pushing and committing and iterating. This is basically just code dumps and use at your own discretion here. So it seems that they use iron depth as the monocular depth estimation. Okay. Surface normal. Iterative refinement of single view depth using surface normal and its uncertainty. I like this. I like MIT license, MIT license. All of these are MIT license, which is good to see. Conda, the environment, management, also using Conda. Conda's more and more popular. What kind of dependencies do we have here? These guys don't even have a requirements.txt. What? Pip install r/requirements.txt. Where is the requirements.txt? Ah, here we go. All right, what you got? You got Torch 1.2, you got Torch Vision, OpenCV, PyTorch Lightning. Okay, that's cool. What else you got here? OmegaConf. This is cancerous. Unpopular opinion, but OmegaConf is crap. Plotly. Okay, nothing else really here. Got your diffusers. This is your got here. Comma, contour, config argparse. Is this like another OmegaConf kind of thing? Also using diffusers. Hugging Face Hub. Got your Jupyter notebook, IPython, Jupyter, matplotlib instead of plotly. You got CUDA, of course, also OpenCV, Python image library. Got PickleShare, I guess, for pickling models. Pickles are security vulnerabilities, BTW. Be very dubious around pickle. Turnians. The request library. This one has a lot of dependencies. Got Torch, a bit more updated version of Torch. But neither of these use Torch or 2.0, right? So PyTorch 2.0 still hasn't hit the research community. Got transformers as well. Okay. Okay. A very large learning rate, especially for something like 100,000 steps, 10,000 steps. Yeah, what is this Obgiverse? Red Roll, Jade Sword. These are pretty good little models. Some of these look complicated though. This is probably like gigabytes. Right? Like some of these probably extremely detailed. You have tags, you have name, description. They already have a Cybertruck. Order of magnitude larger than all previous 3D object datasets. Who actually made this? Is this Sketchfab? Visual diversity. Obgiverse is created by the prior team at the Allen Institute for AI. Allen Institute for AI is basically, there was two Microsoft founders. It was Bill Gates and then it was this other guy. And when he died, I think he's dead, I'm not sure, but when he died, he donated all his money to this Allen Institute for AI. Let me make sure. Allen, Bill Gates, Paul Allen. Yeah, he's dead. Okay. But basically, this guy has Bill Gates money, right? Like this guy has just as much money as Bill Gates from Microsoft, and then he put it all into Allen Institute. Maybe not all of it, but a significant chunk of it. Damn, dude, this guy like also bought a bunch of sports teams, made a bunch of films. Yeah, there you go. Allen Institute for Brain Science, 500 million to the institute, and then Allen Institute for Artificial Intelligence. Damn, I didn't know he had so many of them here. He has Allen Institute for Cell Sciences too. But okay, cool. Got some people here. This Explorer for documentation. What is the license for this? Under the ODC by 1.0. Open Data Commons Attribution License. This is like overly complicated. I just need to know if I can use this to, let me see if I look at commercial. These rights explicitly include commercial use and do not exclude any field of endeavor. Perfect. Okay. So here you go, guys. Use this. This is perfect. Look at all these 3D files, and you can use them in your startup. You can use them to develop your novel AI algorithm, and then sell that AI algorithm. So there you go. I mean, this is kind of sketch, though. Isn't this like a character in a video game, Syndra? You have a character from a video game, and then commercially, you have a commercial license. Like what? I don't know. Copyright is extremely complicated, and it's getting even more and more complicated by the day as people are creating kind of like derivative works on derivative works on derivative works, and it's kind of like this infinite chain of no one knows what the hell the original author of anything is. Spherical coordinate system. We use a spherical coordinate system to represent camera locations and their relative transformations. That's interesting. So spherical coordinate system, obviously different from a Cartesian coordinate system, right? In a Cartesian coordinate system, you have x, y, z, and then you usually represent the rotation of something with a rotation matrix. But in a spherical coordinate system, you represent the position of something with these three angles, right? Psi, theta, and then r, the distance from the center. So obviously in this paper, right, they're conditioning a generative model. Ooh. Ooh. Ooh, come here. Ooh. Who's gonna say hi? Say hi, Petit Boo. You gonna meow for the stream? Okay. Yeah, what was I saying? Yeah, that there's a lot of different ways to represent the position of something in 3D space and the rotation of something in 3D space. You have these matrices, you have different coordinate systems, you also have things like quaternions, right? And I've never actually really seen like a super deep dive on which one of those different ways of representing position in space is the best, right? Because at the end of the day here, they're conditioning this latent diffusion model on the rotation and translation information, but the actual, like how you're actually feeding that into a neural net is still like somewhat unclear to me. Like you could be feeding the quaternions, you could be feeding the quaternion in the normalized position, you could be feeding the position in spherical coordinates, and then also the position in Cartesian coordinates, right? You could be feeding multiple different representations of the same data at the same time. And I'd love to see at some point someone that does like a big ablation study on different types of different representations for position and rotation, and see which ones actually provide the best signal for a neural net to learn from. If anybody knows of any paper that does that, I'd be super happy to figure it out and learn more, but just a meta point. All right, I think we have sufficiently exhausted this. Maybe not. This is kind of a short stream, but hopefully you guys found some of that useful or interesting. Let me know if there's anything else you want to do, and if not, thanks for listening.